Imagine watching a car drive along a winding road. You can see where the car is, but the more interesting question is this: how fast is it moving right now? That idea is the heart of derivatives. A derivative measures how quickly something changes at one exact moment. It can tell us the speed of a car, the growth of a population, the slope of a curve, or the moment a business is gaining customers fastest. And the surprising part is that derivatives begin with something very simple: a slope. You already know how to find the slope of a straight line. You measure how much it rises, then divide by how far it moves across. But a curve does not have one slope. At the bottom of a curve, the slope may be zero. As the curve rises, the slope becomes positive. If the curve falls, the slope becomes negative. So how can we find the slope at one exact point on a curve? We start by choosing two nearby points. Draw a line between them. This is called a secant line. Its slope tells us the average change between those 2 points. Now move the second point closer and closer to the first point. The secant line keeps rotating. As the gap becomes tiny, the line settles into one special direction. That final line only touches the curve at the point we care about. It is called the tangent line. The slope of that tangent line is the derivative. So a derivative is not magic. It is simply the slope of a curve at one exact moment. Now let us solve a real example. Suppose we have a function called f of x. It is x squared plus 3x minus 2. Our goal is to find its derivative. To do this quickly, we use the power rule. The power rule says this: bring the exponent down in front, then reduce the exponent by 1. For x squared, the exponent is 2. Bring the 2 down in front, then reduce the exponent from 2 to 1. So the derivative of x squared is 2x. Next, look at 3x. You can think of x as x to the power of 1. Bring the 1 down in front. 1 times 3 is 3. Then reduce the exponent from 1 to 0. Anything to the power of 0 becomes 1. So the derivative of 3x is simply 3. Finally, look at minus 2. Minus 2 is a constant. It does not move when x changes. The derivative of every constant is 0. Now combine the results. The derivative of f of x is 2x plus 3. That is the answer. But what does it actually mean? Let us choose a specific point. Say x equals 2. First, find the original height of the curve at x equals 2. 2 squared is 4. 3 times 2 is 6. 4 plus 6 minus 2 gives us 8. So the curve passes through the point 2, 8. Now find the derivative at x equals 2. 2 times 2 is 4. 4 plus 3 is 7. That means the slope at the point 2, 8, is 7. At that exact moment, the curve rises 7 units for every 1 unit it moves to the right. On the graph, we can draw a tangent line through the point 2, 8. That line touches the curve and points upward with a slope of 7. This is what derivatives do. They turn a curve shape into an instant answer. They tell us what is happening now. If a position graph describes where a car is, its derivative describes the car's velocity. If a velocity graph describes how fast the car moves, its derivative describes acceleration. If a business graph shows total users, its derivative shows how fast new users are arriving. If a mountain trail is drawn as a curve, its derivative tells you how steep the path is at your exact location. The original function tells you the position. The derivative tells you the change. And that is the big idea. When you see a curve, do not think of it as one fixed shape. Think of it as thousands of tiny slopes. At every point, the derivative reveals the direction and speed of change. For x squared plus 3x minus 2, the derivative is 2x plus 3. At x equals 2, the slope is 7. And now you know exactly what a derivative is. It is the tool that measures change at the moment it matters most.